Welcome to the Deep Dive. We're the show that, well, we don't just skim the surface, do we? We really try to plunge right into the hidden currents of knowledge.
We do. Pulling up those unexpected treasures, hopefully.
Exactly, and giving you that shortcut to being truly well-informed. Today, we are diving headfirst, really deep into the DNA, you could say, of high-performance buildings.
Yeah, the cutting edge of green building standards. It's moving fast.
It really is. Specifically, we're going to unravel the intricate layers of EAc3 BD+ CV5, and particularly its focus on enhanced energy efficiency.
That's EAc3, for those keeping score at home. Enhanced Energy Credit 3.
Right, EAc3. We're framing this deep dive as your custom-tailored guide. We've got a stack of sources, research, our own notes here, all to help you understand precisely how buildings can, well, drastically cut their energy use.
And their carbon footprint, which is just so critical right now.
Absolutely. So whether you're maybe prepping for a big meeting on sustainable development, or you're just trying to catch up on the latest in eco-conscious design.
Or maybe you're just curious, about how we actually build a better future.
Yeah, exactly. This deep dive, it's designed to equip you with knowledge that's not just insightful, we hope, but genuinely actionable.
Practical stuff.
Our mission today, unpack how projects can earn those really significant points in LEV5 by achieving genuinely deep energy savings. And crucially, why this matters so much more than just getting a certificate.
It goes way beyond the plaque on the wall.
It really does.
Yeah.
Now, before we properly dive in, if you're as fascinated by, how we can build a more sustainable future as we are.
And we assume you are if you're listening.
Yeah, probably. Make sure you hit that subscribe button because you really won't want to miss our next deep dives into this incredible world. It's full of innovation, full of impact.
Okay, let's get into it. EAc3.
Okay, let's unpack this. EAc3, Enhanced Energy Efficiency. This sounds like, the powerhouse credit in LEED BD+C CV5 for new construction, doesn't it?
Oh, absolutely. It's not just a minor tweak. This isn't about nudging efficiency up just a tiny bit. It's about pushing buildings way beyond the minimum energy requirements. Think of it as a foundational element, really.
Foundational, okay. And it offers, what, up to 10 points?
A full 10 points, yeah. Which is substantial. That's for projects that achieve really significant reductions in their energy consumption.
And that naturally leads to lower environmental impacts too, right?
Exactly. The two go hand in hand. And just to put those 10 points in perspective, that is a huge chunk of the total points needed for any ELEED certification level: bronze, silver, gold.
But here's the kicker, isn't it? For the top tier, for LE Platinum.
Ah, yes. For platinum, it gets really critical. You need a minimum of 8 points just from this one credit, EAc3. 8 out of those 10 impossible.
So 8 points minimum for platinum. That really tells you everything, doesn't it? About how central, how indispensable energy efficiency is to the definition of a high-performance building in LEV5.
It absolutely does. It signals that you cannot achieve the highest level of green building recognition without tackling energy head-on and aggressively. It's truly at the heart of what we call carbon-conscious design.
A direct lever, you could say, for mitigating climate change in the built environment.
Precisely. Because buildings are such a huge piece of the puzzle globally when it comes to energy and emissions.
So what's truly fascinating here, you mentioned earlier, isn't just the points tally, is it? It's the intent behind it.
Exactly. The points are the mechanism, but the intent behind EAc3 is profound. It's not just a checkbox exercise, not at all. It's a strategic push from the U.S. Green Building Council.
Strategic in what way?
Well, it actively encourages project teams, right from the earliest concept stages through design all the way to operation, to really minimize energy use, fundamentally minimize it.
And that initial minimization, it doesn't just stop there, does it? It ripples outwards.
It cascades. That's the perfect word. It cascades into this whole host of broader systemic advantages that go way beyond just the building's own energy meter.
Okay, so what are those specific goals? What's the roadmap here?
The goals are incredibly clear and, frankly, quite ambitious. First, obviously, is to aggressively minimize overall energy use. That's the core.
Step one.
But from that, you get direct ripple effects. Less energy demand means, naturally, a significant reduction in resource extraction. Less need to mine coal, drill for gas, process fuels.
Makes sense. Less demand, less extraction.
Right. It also leads to a really dramatic reduction in air pollution. Think about it. Traditional power plants, especially fossil fuel ones, they're major sources of smog, acid rain precursors, particulate matter. things that directly impact public health.
Yeah, especially in urban areas.
Absolutely. And then, perhaps the most critical piece in today's climate context, it directly reduces greenhouse gas emissions. That's fundamental to combating climate change.
So it's really designed as a mechanism to speed things up.
Exactly. To accelerate the transition to a clean, low-carbon energy future, it makes EAc3 an absolutely indispensable pillar for a truly sustainable built environment. It's about building smarter, fundamentally, so our planet can, breathe a bit easier.
Okay, so if we step back for a moment, let's look at the bigger picture. What does all this mean? Because as you've laid out so clearly, it's definitely not just about, say, a building owner saving a few quid on their utility bills.
Oh, absolutely not. While the cost savings are definitely a powerful motivator, and they are significant,
Sure, money talks.
it does. But those savings are really just the visible tip of a much larger, much more impactful iceberg. The broader benefits are incredibly crucial. They touch on environmental, economic, even social dimensions that often get overlooked.
Like what? Give us some examples.
Well, consider this staggering statistic. Buildings globally are responsible for nearly 40% of total energy consumption and around 30% of global greenhouse gas emissions. That's huge.
40% and 30%. Wow.
Yeah. So when just one building achieves deep energy efficiency through strategies aligned with the EAc3, it's not just a point on a scorecard. It's a measurable dent in that colossal global footprint.
So it directly fights climate change by cutting those operational carbon emissions, the emissions from the power plants supplying the building.
Exactly. And it doesn't stop there. Highly efficient buildings also dramatically reduce the strain on our energy grids.
Ah, that's interesting. How so?
Well, think about peak demand periods. A scorching summer afternoon when everyone's AC is blasting, or a freezing winter morning. That's when grids are most stressed, most vulnerable to failure.
Right, potential brownouts or blackouts.
Precisely. Highly efficient buildings need much less power during these critical times. They act almost like miniature power plants in reverse. They negawatts, saved watts. This enhances energy security and reliability for everyone connected to that grid.
So fewer disruptions for homes, businesses, hospitals.
Exactly. It helps avert those grid overloads, which means fewer disruptions for essential services in our communities. That's a huge community benefit.
And what about inside the building itself, for the people actually using it?
Well, the advantages extend right inside the walls, too. Efficient design almost always leads to improved indoor comfort. And interestingly, better building resilience.
Resilience. How does efficiency link to resilience?
Think about a building with superior insulation, high-performance windows, maybe triple glazed, and a really well-sealed envelope. It maintains stable indoor temperatures much more effectively.
Fewer drafts, fewer hot spots, just more comfortable overall.
Exactly. More pleasant, more productive for occupants. But that same thermal stability makes the building inherently more robust against external changes.
Like extreme weather or power outages.
Precisely. A well-sealed, super-insulated building will stay cooler during a heat wave or warmer during a cold snap for much, much longer than a standard leaky building, even if the power goes out. It provides a safer, more habitable refuge.
That's a really important point, especially with climate change making extreme weather more common.
It's an often underestimated aspect of sustainable design. And finally, there's the critical piece of future-proofing the investment itself.
Okay, protecting the asset value.
Exactly. Buildings are incredibly long-term assets, right? They stand for 50, 75, maybe 100 years or more. By designing for enhanced energy efficiency now, owners gain huge protection against future energy price volatility.
Because their operating costs will be lower and more predictable.
Much lower, much more predictable. As energy sources potentially become scarcer or global events disrupt supply chains, efficient buildings are far less vulnerable to soaring operating costs. Plus, they adapt more easily to evolving regulations.
Like carbon taxes, stricter building codes. Things that are definitely coming down the pipeline.
They're already here in many places and getting stricter. A building designed to LEED V5 EAc3 standards isn't just compliant today, it's likely already ahead of the curve for regulations 5 or 10 years from now.
Which means fewer costly retrofits later on.
Exactly. And it consistently maintains a higher asset value in a market that increasingly demands sustainability. So, these benefits are truly comprehensive. They impact owners, yes, but also occupants through better health and comfort.
And communities through a more reliable grid and cleaner air.
And even the broader economy through reduced energy dependence and spurring innovation in green technologies. It's a win-win-win scenario.
That's a really compelling picture. It's not just one building in isolation, it's how it fits into and strengthens this much larger system.
Okay, so we've painted the vision, the why. But now, for anyone listening who's involved in projects, architects, engineers, developers, the big question is the how.
A practical roadmap.
Exactly. How do you actually translate these ambitious goals into measurable, certifiable points within LEED V5? How do you get those 10 points?
Right. And that brings us squarely to the mechanics of the credit. The primary route, the main highway to earning these points under EAc3 is option 1, the prescriptive path.
Okay, the prescriptive path. This option is where the bulk of the points are, potentially earning a project anywhere from 1 point all the way up to the full 10 points. It's the real cornerstone for achieving those deep energy savings LEED 5 is aiming for.
And its focus is on.
It focuses squarely on what LE calls regulated energy loads.
Okay, regulated energy loads. That sounds a bit technical. What exactly falls under that umbrella? I'm guessing it's the big stuff.
It is indeed the big stuff, the heavy hitters in terms of energy consumption. Regulated loads are basically the major energy consumers that are typically controlled or managed by the building's core systems.
Like heating and cooling.
Exactly. We're talking about the big four. Space, heating and cooling, keeping us comfortable. Ventilation, bringing in fresh air. Interior and exterior lighting. And domestic water heating for showers, sinks, etc.
So the essentials for operating a building comfortably and safely.
Pretty much. And in most commercial or institutional buildings, these categories combined, they represent a huge slice of the pie. Easily 60%, sometimes 80%, or even more of the total operational energy use.
Wow, so tackling these really gets you the biggest bang for your buck in terms of savings.
Absolutely. You're hitting the biggest targets right away, like taking a super efficient axe, as you said, right to the root of the building's energy consumption.
Okay, so under this prescriptive path, how do projects actually demonstrate savings in these regulated loads?
Well, under Path 1, which covers regulated loads and offers 1 to 7 points, projects essentially have two main ways, two cases, to show compliance and earn those points. It depends on their design approach and how they want to document it.
Two cases. Okay, what's the first one?
The first, and often the most, let's say, detailed approach is Case 1, modeled energy use compared to a baseline.
Energy modeling. We hear a lot about that.
Yes, and this is where sophisticated energy modeling software really comes into play. The project team creates a detailed digital twin, essentially a simulation of their proposed building's energy performance.
How detailed are we talking?
Incredibly granular. It accounts for everything. The building's precise orientation on the site, how it faces the sun, the thermal properties of all its envelope materials, the R value of the insulation, the U value and solar heat gain coefficients of the windows. It includes the specifics of the HVAC systems, the efficiency of the lighting design, even things like anticipated occupancy schedules and how people will use the building.
So a really complex simulation.
It is, and the performance of this proposed hopefully high-performance design, is then rigorously compared against a baseline building.
A baseline, what's that based on?
It's a hypothetical building, identical in size, shape, orientation, and function, but designed to just meet the minimum energy code requirements. And that baseline is typically modeled according to a widely recognized standard, most likely ASHRAE 90.1.
Okay, ASHRAE 90.1. That name pops up constantly in green building. Quick primer, why is it the benchmark?
Sure. ASHRAE 90.1, it's published by the American Society of Heating, Refrigerating, and Air Conditioning Engineers. It's essentially the industry's benchmark standard for energy efficiency in commercial buildings, at least in North America, and it influences standards globally.
So it sets the minimum bar.
Exactly. It sets minimum requirements for the energy efficiency of building envelopes, HVAC, lighting, water heating, pretty much all the regulated loads we just talked about for most buildings except low-rise residential.
So when you model against an ASHRAE 90.1 baseline, you're basically asking.
You're asking, how much better is our proposed design compared to a standard minimum building?
Yeah.
And ASHRAE 90.1 itself gets updated regularly, becoming progressively stricter over time.
Pushing the baseline higher.
Constantly pushing it higher. So the challenge and the opportunity for projects chasing EAc3 points is not just to meet that baseline, but to significantly beat it.
And the more you beat it, the more points you get.
Precisely. It's a direct correlation. Deeper percentage reductions in your modeled regulated energy loads compared to that baseline translate directly into more points, up to the maximum for this path.
Can you give a quick example?
Sure. Imagine you model a standard office building, typical insulation, maybe standard double-pane windows, a conventional rooftop HVAC unit. Then you model your proposed design. super insulated walls, maybe R40 instead of R20, triple glazed windows with special coatings, a highly efficient heat recovery ventilation system.
Okay.
The modeling software then calculates the energy use for both, hour by hour, for an entire year, accounting for weather data. It quantifies exactly how much energy in kilowatt hours for electricity, therms for gas your design saves compared to the baseline.
And that percentage saving dictates the points.
That's right. And the beauty of modeling is that it's iterative. You can test different options. What if we upgrade the windows more? What if we use a geothermal heat pump instead? It allows designers to optimize the design before construction starts.
Finding the sweet spot for investment versus savings.
Exactly. It guides truly informed design decisions. It's like having maybe not a crystal ball, but a very sophisticated simulator for your building's future energy bills.
That makes sense. It highlights the power of data-driven design. Okay, so that's case one, the modeling approach. What about the second case you mentioned?
Yeah.
Case two, prescriptive system performance improvements. This sounds different.
It is different. It's designed to be a more straightforward, you might say plug-and-play approach for certain systems or components.
Less complex modeling.
Potentially, yes. It offers a valuable alternative, especially for projects where maybe doing a full whole building energy model isn't feasible, or perhaps not desired for every single component check.
So instead of modeling the whole system,
Instead of modeling the entire building's energy flow from scratch, this case involves following certain predefined efficiency upgrades or selecting specific pieces of equipment that meet a known pre-qualified performance level.
like choosing from a menu of high-efficiency options.
Kind of like that, yeah. Think of it like this. For your lighting system, instead of modeling illuminance levels and power density for every single room and fixture, you might simply choose to install an all-LED lighting package that's already been certified by, say, Energy Star or the Design Lights Consortium to meet a certain high-efficiency standard.
Okay.
Or for your HVAC, you might select a specific type of high-efficiency chiller or a variable refrigerant flow VRF system whose performance data is well documented and known to exceed baseline requirements by a certain amount.
So the equipment itself basically qualifies you for points.
If it meets the prescriptive criteria laid out by LEED, yes. By its inherent design and published performance data, it automatically qualifies for a certain level of points under these prescriptive guidelines.
That sounds much simpler, potentially.
It can be. It offers a more streamlined, often less resource-intensive path to earning points for specific, high-impact system upgrades. It recognizes that some technologies are just inherently efficient.
Providing a clear route to get credit for using them, without needing a complex model just for that one piece.
Precisely. The exact point allocation, as the source notes mention, is defined in detailed tables within the LED reference guide. We don't have those specifics here, but the principle is the same. The more significant the improvement, whether proven through modeling or achieved by meeting a tough prescriptive standard, the more points you earn.
It adds flexibility, which seems key.
Flexibility without compromising the end goal of deep energy savings.
So that really leads to a crucial question, doesn't it? Why have both? Why offer both a modeled path and a prescriptive path? They seem to aim for the same thing using different methods. Is one better?
That's a really good question. And no, one isn't inherently better. It really boils down to providing flexibility and, importantly, making high-performance design accessible to different kinds of projects.
Catering to different needs and resources.
Exactly. Some projects, particularly larger, more complex ones, or those really aiming for cutting-edge innovation, they genuinely benefit from the deep dive, the granular detail, the optimization power that whole building energy modeling offers.
It lets them fine-tune everything.
It lets them understand the complex interplay between systems, how improving insulation might let you downsize the HVAC, like we discussed. Modeling is a powerful tool for that kind of integrated design and innovation, pushing beyond standard solutions.
But not every project needs that level of complexity.
Right. For smaller projects, maybe tenant fit-outs or renovations where you're just upgrading specific systems within an existing building, the clear, unambiguous guidelines of the prescriptive path can be much more efficient and cost-effective.
A straightforward checklist, almost.
In a way, yes. It provides a clear roadmap.
Yeah.
Use this type of equipment, meet this standard, get these points. It avoids the potential overhead and the need for specialized modeling expertise, which might be a barrier for some smaller teams or budgets.
So it streamlines the process for them.
It does, while still ensuring they contribute meaningfully to energy efficiency by using proven, high-performance components. So both paths drive towards the same critical goal, enhanced energy efficiency, but they intelligently cater to different project scales, complexities, and resources.
Ensuring a broader range of projects can aim high on sustainability.
Exactly. It democratizes access to achieving significant energy savings under LEED.
That makes a lot of sense. That flexibility is smart. Okay, so we've spent a good bit of time on the regulated loads, HVAC, lighting, hot water, the big energy hogs. But we know a building's energy story doesn't end there, right?
Not at all.
LED V5, building on what V4.1 already did, smartly expands the scope. It looks beyond those core systems to capture savings in other areas that are often overlooked but can add up.
Absolutely. And if we connect this back to that bigger picture, addressing these other loads, what LED calls unregulated loads, is really critical for a truly holistic approach.
Unregulated loads. Okay, what falls into that category?
Well, these are energy uses that aren't typically covered by the building's main energy code requirements for systems like HVAC and lighting. They're often related to specific functions or occupant activities within the building.
So not part of the core building systems per se.
Exactly. But they can have a surprisingly significant impact on the building's total energy footprint. In a modern plugged-in office building, for example, these unregulated loads can easily account for 20, maybe even 30% or more of the total electricity consumption.
20 to 30%. That's substantial. What are we talking about specifically?
Broadly, two main categories. First, there are process loads. This is energy used by specialized equipment that's essential to the building's specific function. Think about the hum of servers in a data center.
Huge energy users, data centers.
Massive. Or the constant up and down of elevators and escalators in a tall building. Or all the equipment in a commercial kitchen. Big ovens, walk-in refrigerators, powerful ventilation hoods. These aren't heating the space, but they use a lot of power.
Right. And the second category?
The second is plug loads. This is basically everything plugged into an electrical outlet.
So computers, monitors, printers.
Chargers, coffee makers, desk lamps, maybe specialized lab equipment, audiovisual systems. The list goes on and on.
The everyday stuff we use.
Exactly. And while one laptop doesn't use much power, multiply that by hundreds or thousands of workstations in a large office.
It adds up really fast.
It adds up to a substantial, often unmanaged, energy drain. So LED V5 incentivizes efficiency here, offering potentially another 1 to 2 points in EAc3 for addressing these unregulated loads.
How do you even tackle efficiency for things like elevators or coffee makers?
Well, for process loads, it's about selecting efficient equipment from the start. Choosing Energy Star-rated commercial kitchen appliances, for instance, or specifying elevators with regenerative drives, ones that actually capture energy when the elevator cab is descending and feed it back into the building's electrical system.
Wow, elevators generating power.
Some advanced ones do, yeah. For plug loads, it's often about both technology and strategy. Using smart power strips that automatically cut power to devices in standby mode overnight, or when a workspace is vacant.
Or implementing policies and education for occupants about unplugging chargers.
Exactly. And specifying energy-efficient office equipment across the board. Even seemingly small things, when multiplied, make a difference. It's about recognizing every source of energy consumption and finding ways to optimize it, not just the big, obvious systems.
That holistic view again. Okay, what's next after unregulated loads?
The next pathway really gets into the brains of the building, as you put it earlier. It's about operations and controls.
The smart technologies and operational strategies, making sure the building doesn't just look efficient on paper, but actually runs efficiently day to day.
Precisely. This path, also typically worth 1 or 2 points, is all about ensuring the building performs as designed and then continuously optimizes that performance over its entire life. It brings in the operational intelligence.
What kind of things are included here?
It's a suite of elements. We're talking smart building technologies, the whole Internet of Things, IoT ecosystem within a building, sensors everywhere, measuring temperature, humidity, CO2 levels, occupancy, light level.
Collecting vast amounts of data.
Vast amounts of real-time data. And that data feeds into advanced controls. These aren't just simple thermostats anymore. Think complex algorithms that optimize HVAC schedules based on actual occupancy detected by sensors, not just fixed timers.
So only heating or cooling a space when people are actually there.
Exactly. Or dynamic lighting controls that automatically dim the electric lights near windows when there's plenty of natural daylight, saving energy constantly throughout the day. Or turning off lights in conference rooms automatically when they're empty.
Preventing that wasted energy. What else?
Submetering is another vital component.
Submetering. Monitoring specific areas.
Yes. Instead of just having one main utility meter for the whole building, submetering involves installing additional meters to track energy use at specific points, maybe floor by floor, or for specific high-energy tenants like a data center, or even for distinct systems like lighting versus plug loads.
Why is that useful?
Because that granular data lets building managers see exactly where the energy is going. It helps identify waste, spot anomalies like equipment running when it shouldn't be, and pinpoint opportunities for savings that would be totally invisible with just one main meter.
Makes sense. You can't manage what you don't measure.
Precisely. And ultimately, all of the smart tech, the advanced controls, the submetering data feeds into operational optimization. It's about continuously fine-tuning all the building systems for peak performance based on real-world conditions and actual usage patterns, not just theoretical design assumptions.
And that leads to this idea of continuous commissioning.
Exactly. Continuous commissioning. It sounds technical, but the concept is simple.
Give us the simple version. It sounds like an ongoing health check.
That's a great analogy. Think of it like this. Most buildings get commissioned once, right at the very beginning when they're built, to make sure everything starts up and works correctly according to the design intent.
Like a pre-flight check.
Kind of. But then, over time, things drift. Occupancy patterns change, equipment ages. Maybe someone overrides control settings and forgets to change them back. The building's performance slowly degrades.
Performance drift. I like that term.
Yeah. Continuous commissioning, enabled by a sophisticated building automation system, or BAS, is about preventing that drift. It means ongoing automated monitoring and optimization of the building systems after occupancy throughout the building's life.
So it's constantly checking and adjusting.
Constantly. Sensors collect data, the BAS analyzes it against expected performance benchmarks, and then it either makes automatic real-time adjustments, maybe tweaking airflow slightly, or it flags potential issues for the facilities team to investigate, like, hey, energy use on the third floor jumped unexpectedly last night.
So it's proactive, not just waiting for something to break or the energy bill to spike.
Totally proactive. It ensures the building keeps running at its most efficient, maximizing those energy savings year after year. It's truly data-driven decision-making in action, adapting constantly to reality.
Very smart. Okay, one more pathway you mentioned earlier, renewable readiness. This one sounds really forward-thinking. Designing for the future, literally.
It really is about foresight. It's about designing buildings today so they are ready for the future of clean energy production, even if the actual renewable energy systems like solar panels aren't installed on day one.
And that gets you points, just being ready.
Yes, typically up to 1 point. A lady recognizes the huge strategic value in this kind of future-proofing.
What does being renewable ready actually entail in practice?
Primarily, it focuses on making it easy and cost-effective to add solar, photovoltaic, PV panels later on, but the principles could apply to other future technologies too. It means having solar-ready rooftops.
What makes a roof solar ready?
Several things. First, the roof structure itself needs to have adequate structural capacity. It needs to be strong enough to easily support the added weight of solar panels and their mounting systems without needing expensive structural reinforcement down the road.
So planning for that load from the beginning.
Exactly. Second, you need sufficient, clear, usable roof space. That means designing the roof layout to minimize obstructions like large HVAC units, vent pipes, skylights in the areas best suited for solar exposure, usually south-facing in the northern hemisphere. You don't want things casting shadows on your future panels.
Makes sense. Shadows kill efficiency.
They do. And third, you need the appropriate electrical infrastructure already in place.
Like wiring.
More than just wiring. It means things like installing electrical conduit pathways from the roof down to the main electrical room, even if the wires aren't pulled through yet. It means ensuring there's adequate physical space allocated in the main electrical panels to easily add the breakers and connection points for a future solar array.
So all the prep work is done.
All the difficult, disruptive, and often expensive prep work is done during initial construction when it's much easier and cheaper. Imagine trying to add solar panels 10 years later to a roof that wasn't designed for the weight, or having to drill holes and tear open walls to run new conduit through an occupied building.
Yeah, that sounds like a nightmare. Much more expensive.
Massively more expensive, often prohibitively so. So the strategic value here is immense. Even if the building doesn't install solar right away, being renewable ready removes those significant barriers. It makes future adoption much faster, simpler, and far more economically viable.
Especially as the cost of solar keeps falling.
Exactly. It positions the building perfectly to take advantage of that when the time is right, whether that's due to economics, new incentives, or corporate sustainability goals 5, 10, 20 years down the line.
It really is classic future-proofing, ensuring the building stays relevant and adaptable in an energy landscape that's shifting rapidly towards decarbonization and renewables.
It's about building for tomorrow, starting today. A really smart, strategic move.
Okay, that covers the different paths. So let's bring it all together. If a project team is really ambitious, they want to hit that top tier, get those full 10 points for enhanced energy efficiency. What's the secret sauce? It sounds like you can't just pick one thing.
Oh, absolutely not. There's no single silver bullet to get you 10 points. You've hit the key takeaway. It is emphatically about combining multiple approaches. It requires an integrated design process from day one.
A symphony of systems, you called it earlier.
Exactly, where all the different components, the envelope, the HVAC, the lighting, the controls, are designed not in isolation, but to work together synergistically to achieve those truly deep energy savings. Every element has to contribute.
Okay, so what are the absolute key strategies you need in that symphony?
Well, arguably, the foundation, the starting point for everything else is a high-performance envelope design.
Going way beyond the basic code requirements.
Way beyond the ASHRAE baseline we talked about. This is about making the building itself an incredibly efficient container, like a really, really good thermos.
A thermos for the building. I like that. What does that involve?
It involves, first, superior insulation levels in the walls, the roof, under the slab. Minimizing heat transfer, keeping heat in during winter, keeping it out during summer. Second, using high-performance windows. Often triple glazed these days, with specialized low-emissivity coatings and carefully selected solar heat gain coefficients to control solar energy.
Letting light in, but not necessarily unwanted heat.
Precisely, balancing daylighting with thermal performance. And third, and this is crucial, rigorous air sealing, meticulously sealing all the little gaps and cracks in the building envelope to prevent uncontrolled air leakage.
Because drafts waste a ton of energy.
A surprising amount. A leaky building forces your HVAC system to work much harder. So a tight, well-insulated envelope is your first and most effective line of defense. It reduces the heating and cooling load dramatically, which then allows you to potentially downsize other systems.
The synergistic effect again. Okay, envelope first. What's next?
Next, you absolutely need highly efficient HVAC systems. And again, it's not just buying efficient equipment off the shelf, it's smart system selection and design.
Like those heat recovery ventilators you mentioned.
Yes, heat recovery ventilators, HRVs, or energy recovery ventilators, ERVs, are almost essential for top performance. These devices capture maybe 70–80% or more of the thermal energy from the stale exhaust air that you're venting out anyway.
And use it to preheat or pre-cool the fresh air coming in.
Exactly. Instead of bringing in freezing cold air in winter and having to heat it all the way up, you use the heat from the outgoing air to warm it up substantially first. Massive energy savings right there, just on ventilation.
What else on the HVAC front?
Variable speed technologies are critical. For fans, for pumps, older systems often ran at full speed or off. Variable speed means the motors ramp up or down precisely to match the actual heating, cooling, or ventilation demand at any given moment.
Like a dimmer switch instead of just on-off.
Perfect analogy. It avoids that massive energy waste of running full blast when you only need a little bit of conditioning. Huge savings, especially in buildings with varying loads throughout the day.
Okay. Envelope, HVAC. What about lighting?
Advanced lighting systems, absolutely. And this is way beyond just swapping incandescent bulbs for LEDs, although LEDs are definitely the starting point due to their efficiency and long life.
Oh, so what makes it advanced?
Integration with controls. Primarily daylight controls, also called daylight harvesting, using sensors to measure the amount of natural light coming in through windows.
And automatically dimming or turning off the electric lights nearby when they aren't needed.
Exactly. Maximizing the use of free natural daylight. And occupancy sensors, ensuring lights turn off automatically in spaces that are unoccupied, restrooms, conference rooms, private offices after hours.
Eliminating that phantom energy use from lights left on?
Right. It seems simple, but in a large building, it adds up significantly. Imagine that smart office we talked about, where the lights just seamlessly adjust to sunlight and presence all day long. That's advanced lighting.
Makes sense. Efficient and responsive.
Mm.
What about hot water? You mentioned that can be a hidden drain.
It can be. So, efficient domestic hot water systems are key. The trend here is increasingly towards electrification, but using highly efficient electric options.
Like heat pump water heaters.
Exactly. Heat pump water heaters are a fantastic technology. Instead of creating heat with electric resistance, like a toaster,
Which is basically 100% efficient, but that's it. Cop of one.
right, a coefficient of performance, COP of 1. Heat pump water heaters move heat from the surrounding air into the water. They can achieve COPs of 3, 4, sometimes even higher.
So 3 or 4 times more efficient than standard electric resistance.
Tremendous savings potential, especially in buildings with high hot water demand like hotels or multifamily residences. Combining these with smart recirculation controls that only run when needed further cuts waste.
Okay, so we've got efficient envelope, HVAC, lighting, hot water. What else is in the toolkit for maximizing points?
We have to circle back to energy modeling. Its role is critical not just for documenting savings for EA, but for guiding the design decisions from the very beginning and verifying the expected savings.
Using it as an iterative design tool, not just a final check.
Absolutely. It's the tool that lets you simulate the complex interactions. If we improve the windows this much, how much can we reduce the HVAC size? What's the payback on that? It helps you optimize the whole building as a system.
Finding the most cost-effective path to deep savings.
Precisely. It quantifies the impact of different choices, allowing for truly informed decisions about where to invest resources for the biggest energy efficiency payoff. It's indispensable for reaching those highest point levels.
And then ensuring it performs.
Right. That brings us back to the building automation systems, BAS, used for continuous commissioning. Having that smart central control system isn't just about initial setup, it's about that ongoing monitoring and optimization after the building is occupied.
Fighting that performance drift we talked about.
Constantly fighting it, using real-time data to make adjustments, identify problems early, and ensure the building consistently performs at its peak potential year after year. That sustained performance is key.
And finally, looping back.
Looping back to renewable energy readiness, including that solar-ready roof and electrical prep work. While it doesn't save energy now, it's a crucial strategic element for deep decarbonization in the long run, and LE rewards that foresight.
So it really is a combination platter. You need excellent insulation, smart windows, efficient HVAC with heat recovery, advanced lighting controls, efficient water heating, guided by modeling, managed by a smart BAS, and ready for renewables.
That's the blueprint for hitting 10 points. It requires integrated thinking and commitment across the entire design and construction team.
Wow. Okay, so we've really unpacked the layers here, haven't we?
Yeah.
From the core regulated loads in EAc3 to the unregulated stuff, the smart operations, the future-proofing with renewable readiness. But let's step back again. For you, the listener, absorbing all this detail, what's the ultimate takeaway? What's the core message that should really resonate?
That's a great question to anchor on. If we connect everything we've discussed back to the bigger picture, I think the most important takeaway is about a fundamental shift in mindset.
A shift from what to what?
A shift from just meeting the minimum code requirements or doing just enough to get by towards truly designing for efficiency from the outset and then ensuring the building is performing with impact throughout its life.
It's not just about the certificate on the wall.
Not at all. The principles embedded so deeply in LEV5's EAc3, they're not just about chasing points for certification, they are about creating fundamentally better buildings.
Better in what ways?
Better because they're more resilient to climate change and energy price shocks. Better because they're significantly more comfortable, healthier, and more productive environments for the people inside them. Better because they contribute far less to air pollution and greenhouse gas emissions.
And ultimately, more valuable assets.
Exactly. They stand as powerful testaments to responsible stewardship of our planet's resources. It's really about creating buildings that benefit not just the owner's bottom line, but the immediate occupants, the wider community, and the global environment for decades to come.
Building a legacy, not just a structure.
That's a beautiful way to put it, yes.
That really reinforces that core idea from the source material we looked at. Design for efficiency, perform with impact, lead the transition to clean energy.
A powerful mantra.
And it underscores that these principles, even though they're detailed in a technical standard like LAT, They aren't just for the technical experts, the architects, the engineers, the developers.
No, they have broader relevance.
They're really for anyone who interacts with or cares about our built environment, our infrastructure, and the health of our planet. Every decision, from the materials chosen to how a building is operated, has that ripple effect.
It really does. And maybe a final thought to leave listeners with. Consider the cumulative impact. What if this wasn't just for LE Platinum projects?
What if every new building, every major renovation really pursued these deep energy savings, aimed for the maximum points in enhanced energy efficiency?
Yeah. Imagine that future. What would that truly mean for our global energy grids 10, 20 years from now? How much cleaner would the air be in our major cities, where building emissions are often a huge factor?
How much more stable might energy prices become if overall demand was significantly lower, reducing that vulnerability to global shocks or resource issues?
The scale of that potential impact is it's staggering. It points towards a future where our buildings are active partners in sustainability, working with the planet, not against it. And maybe, how might these strategies, born in large commercial buildings, trickle down even further?
Reshaping our homes, our schools, our communities, making truly sustainable living accessible for everyone.
That's the provocative thought. Where could this lead if we truly embrace it?
Food for thought indeed. Well, we certainly hope this deep dive into LEED V5's enhanced energy efficiency, EAc3, has given you some powerful aha moments.
And left you feeling genuinely well-informed about this critical piece of the green building puzzle.
We've explored its crucial role, the different paths to achieving those deep savings, regulated, unregulated operations, readiness, and maybe most importantly, those broad beneficial impacts that go way beyond just the utility bill.
It's a complex topic, but hopefully we've made it a bit more accessible.
We hope so. And if you want to keep exploring the fascinating ways innovation is shaping our world, especially how we can build a more sustainable future,
Which we'll definitely be doing in future deep dives.
then be sure to subscribe to The Deep Dive wherever you get your podcasts. You really won't want to miss what we unpack next in this world of discovery.